So good morning. Welcome to the topic transformers. So today we are going to see about how to design different types of transformers, and how to design the transformer tanks, cooling tanks. So based on the classifications, based on the number of phases, so we have two types of transformers: single phase or three phase transformer. Based on the shape of the magnetic media, we have a core type or shell type transformer. Based on loading condition, so we have power transformer and distribution transformer. So this is single phase core type transformer, and this figure shows the single phase shell type transformer, so which is having a central line. So as far as power and distribution transformer is concerned, so we have a few differences between these two transformers. So in power transformer, always load on the transformer will be at operated near the full load, whereas in distribution transformer it varies minute by minute in a day. In power transformer, generally the machine is designed for maximum efficiency, whereas in distribution transformer the machine is designed at offload of the maximum efficiency. And in case of power transformer, voltage regulation does not arise, because usually it works at full load condition, whereas in distribution transformer voltage regulation is an important factor. And in distribution transformers, they are not equipped with tap changes, whereas power transformers there is a provision of tap changing terminology. Let us see the sizing of the transformer. So let us see a core type transformer. So this is a core type transformer, where here this is the window area and this is the iron area. So this is the iron area AI and this is the window area AW, and this one is the width of the window and this is height of the window. And window space factor, which is defined as KW, is defined as ratio of area of copper in the window, that is area of copper in the window and area of the window, the total area of the window. It should be less than 1. So the output equation of the transformer. So the rating of the transformer, usually it is in kilovolt ampere. So which is given by VI into 10 power minus 3. This is because of 3 ampere, and which is usually in transformer it is V equal to E. So induced EMF, it is equal to EI in 10 power, which is 3 phase. This is for 3 phase, 4.44 mF number of turns current into 10 power minus 3. So this is similar to all the AC machines. Let us see the code design. The net iron area of the leg or limb or core, different textbooks, different design engineers, they call this as in different terminology like leg, limb or core. That is, the area is defined by how much of the flux we need to have inside the core, and how much flux density it is going to withstand, that is pi by V. So this is Weber, this is Weber per meter square. So if it both cancel, Weber cancel, and meter square, it is the area. So for a given area, there are different types of core sections that are used in practice. Now, at present, people are using circular, rectangular and square. So if you see a circular, say for example, if the diameter is 3.56 centimeter, if then the diameter of the core is 3.5, that is area equal to pi d square by 4. And the circumference is pi into d. That is d is 3.56 centimeters, that equals 11.2 centimeters. If you use a square core, which is having the length and breadth of 3.16 mm, then the area is going to be 10 centimeters square, and side of the square is root 10, which is equal to 3.16 centimeters, and the perimeter is 4 times this length, and 3.4 into 3.16, it is 12.64 centimeter. If you use a rectangular core, the area for area 10 centimeter square, the perimeter is 10 plus 1, that is the length into breadth into 2, this one side and this one side. So it is 22 centimeter if the sides of the rectangular are assumed to be 10 centimeter and 1 centimeter. So the most important design aspect in a transformer is designing the tank. This is the tank. So transformer design. So the dimension of the tank depends on type and capacity of the transformer, voltage rating and electrical clearance to be provided between the transformer and tank. Clearance to accommodate the connections and taps, clearance for base and oil above the transformer, etc. These clearances can assume to be between 30 to 60 centimeters in respect to tank height. So this is with respect to tank height, and 10 to 20 centimeters in respect to tank length. So this is the tank length, and 10 to 20 centimeters in respect to tank width. So this width. So this is the length, this is height, and this is the width, and these are the cooling tubes. So the major aspect in design is how far we are going to, how many tubes we are going to insert in a oil or liquid cooling transformers. So let us take that, how to calculate the tank height. It is width of the so this window area height plus 2 times the back iron thickness. This is the yoke, so back iron, plus clearance. The clearance is going to be 30 to 60. It depends on the power rating. It is going to, if it is more power rating transformer, the clearance is more. Less power rating, the clearance is less. For a single phase and 3-phase core and single phase shell type transformers. Whereas for a 3-phase shell type transformer, it is 3 times of your HW plus 2HY plus clearance 30 to 60 centimeters. Similarly, tank length is going to be D, that is this is inner distance, and D external is this is the D external plus clearance, that is 10 to 20 centimeters. As we discussed that the clearance should be, it is in 10 to 20 centimeters. So for a single phase and 3-phase shell transformer, it is going to be 4A, that is sides 4A, sides plus 2 width, 2 times of the width plus clearance. Width or breadth of the tank is going to be D external, that is D external, this one. So this is going to be the D external plus clearance 10 to 20 centimeters for all types of transformer with circular coil. And with a rectangular coil, this is going to be B plus W plus clearance. And the most important thing we need to note down here is the dissipating surface of the tank. So that is ST. The dissipating surface is going to be calculated by 2 HT, that is 2 times of the tank height into length of the tank plus width of the tank. So where the losses, the temperature losses is going to be 12.5 into dissipating surface. Theta is the maximum temperature rise plus 8.78 area of the tube into the base temperature. Width of the stamping and B gross thickness, height of the yoke, distance between the two core leg. So heat gas depleted to the atmosphere from tank by radiation and convection. So the convection coefficient is going to be like this, and the area of the tube is going to be 1.3 times into 6.5 area of the tube into theta, that is equal to 8.78 AT, this one. So 8.78 area of the tube into theta. So number and dimensions of the tube. If the temperature rise of the tank wall is beyond a permissible value of 50 degrees Celsius, then cooling tubes are to be added to reduce the temperature. So how many cooling tubes are added? It is based on the size and width of the tank, as well as the different ways how the tubes are going to arrange, whether it is in a round manner or otherwise in the rectangular manner. Let us solve a problem so that it is easy to understand how to design a cooling tube. So today we are going to design a suitable cooling tank with cooling tubes for a 500 kilovolt ampere 50 hertz 3-phase transformer with the following data. The dimensions of the transformer are 100 centimeter height, 96 centimeter length and 47 centimeter breadth. Total losses is going to be 7 kilowatt. Allowable temperature rise for the tank walls is 35 degrees Celsius, that is theta. Tubes of 5 centimeter diameter are to be used. That is, each tube is going to be 5 centimeter. Determine the number of tubes required and their possible arrangement. So let us take the tank height first. Try to find the tank height, transformer height plus clearance. You can take the clearance between 30 to 60. Here I take 50. And transformer height, it is in the given data. The transformer height is 10 centimeters. So everything I solved in centimeters because the given is in centimeters. If you want to change into SI units, you may change. So 100 plus 50 equals 150 centimeters. So tank length is transformer length plus clearance. So transformer length is given, that is 96 centimeter, and clearance I took here as 14. So it is going to be 110 centimeter. So width of the tank is going to be transformer width or breadth, that is 47, plus clearance. Here I took as that is also between 10 to 20. So here I took 13. So to get a round figure 60 centimeters. So the losses, we know how to calculate the losses. It is 12.5 st theta plus 8.78 AT theta. So the losses are calculated based on this one. So here we need to find what is the dissipating surface of the tank. So the dissipating surface of the tank is calculated by 2HT into LT plus WT. So we know HT, LT, WT. So the dissipating surface is going to be, I just convert everything into meters so that the dissipating surface comes in meter square. So 2 into 1.5, that is with clearance. Remember this one, usually if you calculating the dissipating surface of the tank, that is with the clearance of the tank. So it is 1.5 meters into 1.1 meter plus 0.6 meter equals 5.1 meter square. So the total losses given is 7000 watts. So 12.5, it is in the formula is 12.5. So yes, theta allowable temperature is 35 degrees Celsius plus 8.78 80 into 31. So from this equation, try to find the area of tubes. So the area of the tube from this equation is 15.6 meter square. So note down, this formula is this one. So losses is 12.5 st theta plus 8.78 AT theta. Theta is the allowable temperature rise. Suppose if this theta is not available in the question, then you just take this theta as the room temperature. Then the next step is we need to calculate what is the dissipating area of the each tube. So that is pi into diameter of the tube. The diameter of the tube is going to be 5 centimeter. It's given into average height and length of the tube. So that is pi into diameter of the tube and average length. So it is 0.9 into 1.5. 1.5. So it is going to be 0.212 meter square. So now, based on this dissipating area of each tube and the area of the all tube, if you divide area of the all tube with the dissipating area of each tube, then you get total number of tubes. So that is 15.6 meter square divided by 0.212 meter square, which gives 73.6. It is not possible to make as the fraction, so we need an integer. Either you choose 73 tubes or 74 tubes. Here I choose as 74. If these tubes are placed at 75 centimeters apart from center to center, then the number of tubes that can be provided along 1 centimeter. See here, the length is 110 centimeter. See here, the length is 110 centimeter, the tank length, and the width is 60 centimeters. So the length is 110 centimeters, width is 60 centimeters. So we have totally 74 number of tubes. So if I place these tubes, each tube 75 centimeters apart from center to 7.5 centimeters. So from here to here, If it is 7.5 centimeters apart, then the number of tubes can be provided along 110 centimeter and as 110 divided by 7.5, that is approximately 15, and 60 divided by 7.5 is approximately 8. So here if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So similarly this is 20 tubes in 2 rows, 2 into 13 tubes, 15, 8. So therefore number of tubes that can be provided in one row all around is going to be one row all around is 2 into 15 plus 18, it is 46. Since there are 74 tubes, tubes are to be arranged in second row also. If 46 more tubes are provided in second row, then total number of tubes are going to be 92 and is much more than 74. With 13 and 6 tubes along 100 centimeter, total number of tubes provided will be 2 into 13 plus 6. So which is equals 76. Though 74 are only required. So likewise, see 2 into 13 tube, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 into 2, that is 26 here, here it is 26, and 1, 2, 3, 4, 5, 6, 6. So 6 into 2, it is 12, 12 into 24, 24 plus here it is 52. So it is going to be around 16, 13 plus 6. So it is 76, those 74 are only required. So you need not worry about this two things. You can omit these 2 tubes so that the entire 74 tubes can be placed according to the thing. This is for round circular tubes. Once again I tell, so here now calculate the number of tubes based on area of the total tubes and area of each tube. So area of the total tube divided by area of each tube. So which is going to be around 74. If let us take this is also not fixed. You may take this as your own if it is not available in the question. Suppose if you want to place it in 5 centimeters, then it is also possible to place it in 5 centimeters apart. So this one is not a mandatory thing to fix with 7.5 centimeters. You can use 5 centimeters, 8 centimeters as per your design wish. So we have 110 centimeter length and 60 centimeter width. So in that we need to fix this 74 tubes. So as your own design thinking, you can fix your tubes, you can spread your tubes as your wish. Not only for 13, 6, you can go for either 14, 5 or otherwise 12, 7, anything. Everything you need to make a clearance of some centimeters at each and every edge here. So you can't able to fill at the edge. So you need to give some clearance, say for example 2 centimeters to 4 centimeters. Then based on that clearance, you can fill other tubes as your wish. So no need to stick with the same thing. You can go with some other values also, say for example 12, 7 or otherwise 15, 5. So as per your wish. So 15.5 is also the better thing. So if you have a 15 here, check whether you have a clearance between and reduce the gap between these two. Instead of 7.5, you reduce the gap between 5 centimeters so that you can fill 15 tubes here and 5 tubes here. So that's up to you. So design thing. So you can design your tubes and you can insert your tubes as your wish with the tubes are placed apart from center to center. So this is what the basic cooling tubes design are for a transformer. So this is the most important aspect of a transformer design. So without knowing this cooling tube design, it is not possible to design the transformer core itself, because whatever the core you are going to design for a high power rating, usually the cooling tubes fails, then the entire design is going to be failed. So the design of cooling tubes is going to be a vital part in transformer design applications. So this is the plan showing the arrangement of tubes. So if you count this, this is 13 tubes in one row. So and in two rows it is 26. Similarly here it is 13, here it is 13 as far the design is concerned. And I just strike out this 2 because we only require 74 tubes, not 76 tubes. So whereas as width side is concerned, that is 60 centimeters. So it is 6 tubes in one row. So here the second row contains another 6, it is 12. So total thing it is going to be 24. So in exams also you need to plot this plan which you are going to show the arrangements of the tubes. So this is mandatory for any design of the transformer. So just take down this question and try to solve as your own. If there is any doubt, you may come and discuss with me in my cabin, or otherwise you can put a mail to me, whatever the queries you are having. So thanks for watching.